Hello students, in this video we are going to start current electricity. Okay, and this whole chapter will not be completed in this video. Okay, so it may take 8 to 9 or 10 videos. Okay, so please stay connected, do subscribe the channel, hit the bell icon so that you get notified when the new video will be uploaded. Okay, and if the next part is uploaded already, then it must appear at the end of this video, at the end screen. Okay, just click there, then you get access to the then you will get access to the next video. Okay, next part, right? And if you want to follow me on Insta, this is my Insta ID, OJHALAKHYAJIT. This is my Insta ID 123. You can follow me on Insta. If you need the PDF of the PDF of this chapter, notes of this chapter. Okay, if you need the notes in the form of PDF, then you can send your phone number to this Insta ID. Just send me in inbox. Okay, then I will provide you the PDF of the notes of this lecture, not only of this lecture, of the whole chapter. Okay, so please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you, and don't forget to hit the bell icon. So do hit the bell icon so that you get notified when the new video will be uploaded, right? So now let's start. So current electricity. So what do you mean by current? Current is nothing but flow, right? And when we say electric current, that means flow of charges, right? So now you see, suppose we have a conductor. This is a conductor. We know metals are good conductors, right? So in metal atoms, this is suppose nucleus, and this is the outermost electron. Suppose this outermost electron, or the valence electrons in metal atoms, are loosely bound with this nucleus. Okay, so that's why at room temperature, these valence electrons have enough energy so that they can freely move, right? So that they can freely move randomly. Okay, they have enough thermal energy so that they can freely move. So that's why we used to say that metals contains free electrons, right? So now you see, when we apply an electric field, or you can say, let us if we connect this conductor with a battery, this is positive, this is negative, right? And now you see, suppose this is an electron, right? And this is the nucleus of the atom, and this is the outermost electron. Similarly, we have more atoms, large number of atoms, and this is the valence electron. Suppose this is another atom, this is the valence electron, and these electrons can freely move. Okay, these valence electrons can freely move. So when we connect this conductor to a battery, then these electrons will move towards the positive terminal, because these electrons are negatively charged, right? These electrons are negatively charged. Okay, so now here you see, when this electron you see will move away towards this direction, then this atom will be positively charged. Then, so as this electron is removed, now there will be a void, we used to say hole, and because of that positive charge, Okay, because we know that in neutral atom there are equal number of protons and electrons, which makes the atom neutral. So number of electrons and number of protons are positively charged and electrons are negatively charged, and they are equal in balance in a neutral atom, right? So when electron will be removed from this atom, then it will be positively charged, because now one negative charge is less, right? So as it is positively charged, now this electron comes towards this positive direction, then this atom will be positively charged, and then again this electrons comes towards it, and then again it will be positively charged. So now you can observe that these electrons are coming towards this direction, which is connected to the positive terminal of the battery, and positive charges are going in opposite direction, which is connected to it is going towards the end, which is connected towards the with the negative terminal of the battery. So this flow of charges is nothing but electric current, and we used to consider the conventional current is in the direction of flow of positive charges. Okay, we consider the direction of current towards along the direction in which this positive charges flows. Okay, so in conductor we get electric current due to the motion of these electrons and the holes means the positive charge, right? So now let me define what is it. This is the conductor, and let us consider a cross section of this conductor, and charged particle, amount of charges passing through this conductor is suppose q in time t. Then current in this conductor is given by I is equal to q by t. So we can say that electric current let me write the definition of electric current. So how to define this electric current? So electric current is defined as electric current is defined as the amount of electric charges flowing through any cross section of a conductor per unit time. So this is the definition of electric current, right? So hope you have understood this. Now you see, let me scroll down the page. So now you see, just let me use the black ink. Okay, if Q be the amount of charges passing through any cross section of a conductor in time t, then electric current current in the conductor is given by I is equal to, let me use this blue ink, I is equal to Q by T, right? I is equal to Q by T. So now here one more important thing, let me tell you one more important thing. Now you see, the current through the electric current through a conductor is not, it is not necessary that it is always it will be always steady. Steady means, suppose this is a conductor and this is a cross section. Suppose in the first 1 second, suppose Q amount of charge flows through this cross section. So it is not necessary then that in the next 1 second, that means in the second 1 second, it is not necessary that same amount of charge will flow through this cross section. It may be Q dash. In the next 1 second, it may be Q dash. So in that case, we need to find instantaneous current, right? So how to find that? Suppose let me explain it. Just let me okay. Suppose you see, this is the conductor and this is a cross section. Okay, suppose let me consider that in time t seconds. Okay, so suppose Q amount of charge flows through this cross section, and after t plus del t seconds, at t plus del t seconds means del t times after t, right? So the time interval between these two instants is very small, del t suppose, and at t plus del t time, suppose charge flows through this cross section be suppose Q dash. Okay, and during this interval t2 t plus del t, between these two times, suppose del q dash minus del q, which is suppose q dash minus q, that is suppose del q. Suppose del q amount of charges flows through between these two time interval, between these two time t plus t and t plus del t. That means the time interval is del t. So we need to find the current at an instant t. Then we have to consider this del t is very small. That means if t is suppose 1 second, then t plus del t is suppose 1.000000001 second. That means this 0.001 is the del t. This is very small. So then you see 1 second and 1.0000001 second is so almost equal, right? So then we if we take the charge flows through this cross section between these two time, between these two time, that is suppose del q, and this del t time is the time interval, okay, which is tends to 0. That means very small, right? Then if we divide this by this time interval del t, then we will get the current at t. Okay, because you see the difference between 1 second and 1.0000001 second is very small, right? So in that case, then we used to write instantaneous current at an instant t, that is limit limit del t tends to 0, del q by del t, which can be written as dq by dt, right? So hope you have understood this. So now let me clean this. So let me write this one. If currents are not always steady, okay, are not always steady, so we can define sorry the current uh, at an instant, right, t, at an instant t as I of t, which is current at time t, limit del t tends to 0, del q by del t, which is nothing but dq by dt. So I hope you know this, the differential coefficient del t. So when you write limit del t tends to 0, del q by del t, which is nothing but dq by dt. So now you see here, this del q is nothing but you see the charge, del q is the net charge, flowing across a cross section sorry, I made a mistake, cross section, right, of a conductor during the time interval del t, during the time interval del t, right? So let me highlight this, just let me highlight this formula. Okay, so hope you have understood this. Now you see, let me write one more thing, important thing, that is the direction of electric current. The direction of electric current is given by the direction of flow of positive charges, okay. Remember, we're going to consider the direction of electric current, in which direction the positive charge in a conductor will flow. Okay, so Hope you have understood this. Now let me scroll up. Okay, sorry, let me scroll down this. Now you see, just give me a second. Okay, now you see, hope you know the SI unit of current. SI unit of electric current is ampere, right? That is A, right? So that means 1 ampere current is equal to 1 coulomb charge by 1 second. That means in 1 second, through any cross section of a conductor, if 1 coulomb charge flows through this cross section, then the current in that conductor will be 1 ampere, right? So let me write the definition of 1 ampere. Just wait. Okay, so here you see, so the electric current through a conductor is said to be 1 ampere, is said to be 1 ampere if the rate of charge flow is 1 coulomb per second through the conductor. Right? So hope you have understood this. If you need the PDF of this lecture, then send a message to my Insta ID. Okay, send your phone number and your name and in which college you study. Okay, then I will send you the PDF. Okay, so in the next lecture we're going to discuss about drift velocity and various type of currents as well. Okay, so see you in the next video. Thank you.